Assalamu alaikum dear students. Okay, last time we have discussed very important consequences of Sylow's theorem, and today we are going to discuss very important result which can be seen as a consequence of last results of my last lecture. And what is this? Let G be a group of order PQ, where PQ, P and Q are distinct primes, P greater than Q, and further, if P is incongruent to one modulo Q, then G is cyclic, right? This result is very useful because by using this result, you can directly show that if a given group satisfy these conditions, then it is cyclic, right? So this is very useful. So last time you have proved a theorem that if order of G is equal to PQ and P greater than Q, PQ are primes, distinct primes, then H, which is equal to A power P is equal to 1, is normal in G. Last time you have shown this result, that whenever you have a group of order PQ where P is greater than Q and PQ are distinct prime, then you can always find a subgroup H like this, which is normal in G, corresponding to larger number P. Okay, so here we are using this condition. If P is incongruent to one mod Q, I just want to teach a little bit number theory to you people. We say that A is congruent to B modulo M if and only if M divide A minus B, right? So if M does not divide, similarly, if and only, this means that if M does not divide A minus B, if and only if A is incongruent to B modulo B. So when I am saying that P is incongruent to 1 modulo Q, this means that Q does not divide P minus 1. So simply, when you are saying that P is incongruent to 1 modulo Q, this implies Q does not divide P minus 1. Okay? So if Q is not a divisor of P minus 1, then G is cyclic. Okay? In number theory, there is also a very popular theorem which is called Euler theorem. Euler's theorem. Euler theorem says that A power phi of M is congruent to 1 mod M, where this is in journal. And if you want to write this for P, then A power phi of P congruent to 1 mod P. So here you will write that P does not divide A. Because if P is a divisor of A, then this must be 0 in modulo P. So if this is equal to 1, then of course P does not divide A. And what is phi of P? Phi of P is the Euler's phi function. Euler's phi function. And you know that if P is a prime number, then phi of P is equal to P minus 1. So here, what is phi of P? So one result is A power phi of P is congruent to 1 mod P when A and P are relatively prime. And what is phi of P? Phi of P, a general result for this phi of Pk is equal to Pk minus 1, where P is prime. So if you write 1 for phi of P 1, that is P power 1 minus P power 1 minus 1, which is P power 1. So phi of P is P minus 1. So put here, you will get that A power P minus 1 is congruent to 1 modulo P, which is when A and P are relative prime. If you multiply by both sides, so you are getting A power P congruent to A modulo P. This is also called Fermat-Little theorem, right? So because I want to use a little bit number theory in the proof of this very important result, so that's why I want to teach you a little bit you number theory. So this is the generalized result, Euler's theorem, a power phi m congruous 1 mod m. Here this is true in either case, whatever m is, but if you are taking m as p, then you have to insert the condition that p does not divide a. That is a and p are relatively prime. So this is the Euler's theorem, and this is the Euler phi function. Phi of pk is equal to pk minus pk minus 1. This is the generalized formula for prime powers. And if you put k is equal to 1, then phi of p is p minus 1. So phi of p is equal to p minus 1. Putting here, you will get a power p minus 1 congruous 1 mod p. And if you multiply on both sides, this implies you can write a power p congruous to a mod p when p and a are relatively prime. This is also called Fermat-Little theorem. Now come to proof. Remember, you can have the application of this theorem, which is so easy. Now you take a group of order G is 15. If you take a group of order 15, this is equal to 3 into 5, right? 3 into 5, that is, if you take P is equal to 5 and Q is equal to 3, according to this condition, P is greater than Q, and P, Q are distinct primes, and G is a group of order PQ. So here order of G is 15, that is 3 into 5, you take P is equal to 5, Q is equal to 3, and see here 3 does not divide 5 minus 1, which is 4, that is 3 is incongruent to 1 modulo 5, means 5 is incongruent 1 modulo 3. You see, all the conditions are satisfied. You have order of G is 15, which is 3 into 5. So P is equal to 5, Q is equal to 3, and then 3 is not dividing 5 minus, that is P is incongruent, hence any group of order 15 is cyclic. And you know that this is C15, right? And you know that every group, every cyclic group is abelian. This means that there does not exist any subgroup of order 15 which satisfying these conditions. There does not exist any subgroup of order 15. You know, 15 is 3 into 5, and this can be written in this form. So there does not exist any non-abelian group of order 15. Okay, you know that the group of order 15 is cyclic, and every cyclic is abelian. This means that every subgroup of order 15, every group of order 15 is abelian. This means that there does not exist any group, any non-abelian group of order 15. Okay. Now you can also have some other. You choose 3, Q is equal to 3, and choose P where 3 does not divide that minus 1. If you take 5, we are done. If you take 7, then 3 will divide 7, leave it. If you take 11, you take 11, you take 13, 3 divide 12, and you take 17, you take 17, right? This means that order of G is equal to 3 into 11, 33, 3 into 17, 51, right? These can be written in the form. So every group of order 33 is abelian. There does not exist any non-abelian group of order 33. Now see, 17 minus 1 is 16, 3 does not divide 16, both are different point, and their product is 51. So there does not exist any non-abelian group of order 51, right? Similarly, if you take P, Q 5, then move forward, you take P 7 will work, yes, P minus 1, Q does not divide 6, and also P you take then 11, 11 will not work. because 5 divided 11. So you can take 13. So yes, 13. And so forth. This means that order of G is 35 and then 65. This means that all groups of order 35 or abelian. There does not exist any non-abelian group of order 35. There does not exist any non-abelian group of order 65, right? Because 5 does not divide 13 minus 1. If you take Q is equal to 7, you take P is equal to 11, yes, it will work. Then 13, yes, it will work. Then 17, yes, and so forth. You can find many. So this implies order of G is equal to 77, 91, and so on. So there does not exist any non-abelian group of order 77. There does not exist any non-abelian group of order 91. So that's why I am saying that this theorem is very important. Now I am going to prove this. I will use a little number theory. If you will not get these results of number theory, you can go through any good book of number theory, right? But I'll try to elaborate because I already have told you about congruence relation, and also I have told you about Euler's theorem. Now I will use these two to prove this. Okay, now proof is proof by Cauchy's theorem. Since by Cauchy's theorem, G has groups. G contains elements A, B of order. G contains elements A and B of orders P and Q respectively. Right? You know that Cauchy's theorem says that if P is a divisor of finite group G, whether it is abelian or non-abelian, then G contains an element of order P, right? And since P is a divisor of PQ, so there must be an element A of order P. And since Q is also a divisor of PQ, so there must be an element B of order Q. So you have supposed that A is an element of order P and B is an element of order Q respectively, right? But then you can have subgroups corresponding to these two elements of order P and order Q. So take since by last theorem, since order of G is equal to PQ, P greater than Q, and PQ are distinct primes. So by last theorem, okay, you can see this theorem. You will not write this in the proof, but you know that if order of G is PQ, P is greater than Q, and PQ are distinct primes, then H is equal to A, such that A power P is equal to 1, is normal in G. Okay, see my last lecture. This was the last theorem of my last lecture, that if order of G is equal to PQ, P greater than Q, and PQ are distinct primes, then this H must be normal in G. This H must be normal in G. This means that then B, A, B inverse belong to H, where B belong to K, which is of course a subset of G. You take B as an element of G, then B inverse is an element of H, since H is normal in G. Since H is normal in G. You take, for sake of convenience, B as an element of, because B is an element of G, so even for that element of B, this condition is satisfied, right? But H is generated by A, so this element, since H is cyclic and A is the generator, this means that every element of H is in some power of A. So first you should know the idea that if you are taking any element of a cyclic group which is generated by A, if I am saying that X belongs to H, then X must be some power of A. And since I have shown that B inverse, being H as normal, is an element of H, and H is a cyclic group generated by A, so this element must be some power of A. Hence, B inverse must be equal to AK, where K is less than P, right? So here we claim that K greater than 0, because if K is equal to 0, then B inverse is equal to E, then A is equal to E, but A is the generator, which would be a contradiction, so K must be greater than 0. We claim that, note that K is greater than 0, for otherwise B inverse is equal to A power 0. If K is equal to 0, then B inverse is equal to A power 0, which is the identity. So this implies B inverse is equal to E. So this implies A is equal to E, a contradiction. A was the generator of capital H, that's why A is not equal to E. You are taking a non-identity generator, because identity can generate itself only, right? So since H is a group of order P, so A is not equal to E, and you are given that A is equal to E, hence K must be greater than 0. Hence B inverse will be equal to AK, where 0 less than K less than P. Say this is number 1. Okay, now we will use this. Okay, note that B square AB inverse minus 2. Look at what will happen when you are taking B square instead of B. You will get, this is B inverse, this is B inverse, this is B. I can write this like this. And what is this? This is A power K. You are getting B A power K B inverse. So definition is, you are raising power K of the central element. So again, if you will use this, you will take AK power K. This is the central element, and B inverse. The formula is, you will take raised power K of the central element. So this is equal to AK power K using 1. So this is equal to AK square. And if you continue, then you will see that continue B power Q A B power minus Q, which is equal to A power K power q, right? When you are taking power 2 here, you are taking power 2 here. And by going on similar fraction using the induction, you will see that if you take bq, then k power q. If you take b2, you are getting k power 2. If you will take bq, you will take k power q. But what is this? This is e. This is e, a. This is e inverse, which is a k power q. So this implies a is equal to a power k power q, right? This implies a power k power q minus 1 is equal to 1. But you know that order of a is b. But order of a is b mean that p is the least positive integer sign that a power p is equal to 1. That is, p is the least positive integer such that a power p is equal to e. Hence, e or 1, whatever you are taking. If you have taken 1, you can write 1. If you are taking e, you can write e. There is no problem. So, hence, and you know that there is a result. If a power n is equal to 1, where order of a is n, that is order of a is n, then a power m is equal to 1 if and only if n divide m, right? Any other power can also give you 1, like if the order of omega is 3, then omega 6 is also 1. 1 omega omega square. You take the group 1 to understand the simplest example. 1 omega omega square. Omega cube is equal to 1. Omega 6 is equal to 1. Omega 9 is equal to 1. All are multiples of the order. So that's why a power kq minus 1 is equal to 1, but order of a is p. So this implies p will divide a power k power q minus 1 here, power k power q minus 1, and now you will use the congruence equation. You know, I have told you that okay, this was the power. This was the power of a. And here, a power p was 1. This was the power. So that's why this is the least power. So p will divide this. P is dividing this. And you know that if p divide a minus b, this implies a is congruous to b mod p. Right? So this implies k power q congruous to 1 mod p. But you know that k power phi of p congruous to 1 mod p. Okay, one thing more. By Euler's theorem, phi of p, this is always 1. Here there is no question that phi of p is the least element or not. This is always true. Okay, when k is a primitive root of p, I am using the term primitive root, you can understand. Then phi of p must be the least. But in Euler, we know nothing that whether phi of p is the least element for which you are getting 1. That's why we understand that q will divide phi of p, right? We understand that q will divide phi because k power q congruous 1 and phi of p is the general understanding is the Hash number unless k is a primitive root. That's why you don't have any problem. This is always true beyond the order of k, right? We are not talking about order here, okay? So that's why phi of p is the Hash number lesser than p, that is phi of p is p minus 1. So we understand that if k power q congruous 1 and k power phi of p is 1, we understand that q is the divisor of this number, you know. So this implies, so let's say 1, so 2, So by 1 and 2, this is because Euler's theorem. I have explained before the starting of the proof that k power 5 of p congruous to 1 mod p. You know that p does not divide k. This is understood. Okay. So by 1 and 2, it is clear that q divide phi of p. And you know what is phi of p? This is p minus 1. Q divide p minus, which is, but you are given that q does not divide p minus 1. Okay. That is q divide p minus 1, but we are given that q does not divide p minus 1. Thus the only possibility is because we are doing this through proper stepping, so there is no problem. So you need to find the possibility, because we are not going to contradict something. We are doing in a simple fashion by using the given conditions. So that's why I don't have any problem. Or again, if you're finding some problem, then you will find that this is true, but what is the possibility for which this is true? So the only possibility for which this is true is q is 1. But we are given that q divide p minus 1. That's the only possibility is q is equal to 1. You know that 1 is a divisor of every integer. So 1 can divide p minus 1. So here q is 1. Putting in back, putting in 3, you have this k power q congruous to 1 mod p. Say this is number 3. Putting in 3, we get, this was your k, put k1, so this is k is congruous to 1 mod p. This means that, again by using the simple congruence, this implies p will divide k minus 1, but k minus 1 is lesser than p. Since k is lesser than p, again, but you are doing the simple process, you are using the conditions, so there should not be any contradiction. You need to find the possibility. Thus this is possible only if k minus 1 is equal to 0, because every number can divide 0. Every number is a divisor of 0 except 0 itself, right? Hence we have the only possibility is, k minus 1 is a smaller number, and a larger number can never divide a smaller number. So if a larger number is dividing a smaller number, then that smaller number must be 0. Hence the only possibility is k minus 1 is equal to 0. So this implies k is equal to 1. So putting in, you have b inverse is equal to a k. Put here, we get b inverse is equal to a k, a power 1. We have established that k is equal to 1. There we were using k as the general element, but we have established that through our given informations and using a little number theory, I have shown that k is equal to 1. Thus b inverse is equal to a1. This means that This implies BA is equal to AB. Okay, and you know that if BA is equal to AB, then powers of AB can be rearranged. But then AB power PQ is equal to AB, 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 PQ factors, and you can replace, you can rearrange. This BA can be AB, this BA can be AB. From here, this is so easy to show using this AB is equal to BA. You can write A power PQ into B power PQ. Since AB is equal to BA, this implies A power P power Q, B power Q power P. This is E, E, E. Right. So you are getting an element AB, which is an element of G, whose power PQ is equal to E. So G is a cyclic group generated by PQ. Thus, G is equal to AB sided AB power PQ is equal to E. This shows that G is cyclic. Okay. This is so easy. The proof was very interesting and very elegant. We have used a little number theory to prove this theorem. Okay. What was the idea? Since order of G is equal to PQ, so by Cauchy's theorem, you must get an element of order P, right, and order Q as well. So you have taken two groups H and K. One is A power P is equal to 1 and A power Q is equal to 1. That's the other one. And by the last lecture, the last theorem of last lecture, you please see my last lecture, that is lecture number 17 probably. We have shown that if order of G is equal to PQ, where P is greater than Q and PQ are distinct primes, then you can always find a normal subgroup of order P. That was H. So H is a normal in G. And you take some B belong to G. If H is normal in G, then G inverse belong to H. So instead of G, you are taking B, because B is also an element of capital G. So B inverse must be equal to some element of H, because H is a cyclic group generated by A. So we claim that B inverse is equal to A power K. Now the target is to show that K is equal to 1. Because if you can show that K is equal to 1, then B inverse must be equal to A, that is BA is equal to AB. If BA is equal to AB, then this is so easy. This means that AB is an element of G of order PQ, and if G has an element of order PQ, this means that that element is serving as a generator. This means that G is a cyclic group. So for this you have used techniques and little number theory and one of Euler theorem. You have shown very easily that G has an element of order PQ, so because G is cyclic. Now you can enjoy this theorem. You just take order of G as a product of PQ, where P is greater than Q and Q is incongruent to P minus 1, then G must be cyclic, right? Using that number theory we have established. Okay. The next and last result is today's lecture. Last result is if K is a normal subgroup theorem, normal subgroup finite group G. If K is normal in G, of course, a finite group. If K is normal in G and H is a Sylow P subgroup of K, So the P subgroup of K, then G can be decomposed as K with its normalizer, right? Where N is the normalizer, where N is the normalizer of H in G. Okay. Now what is this? You can decompose a group G like this, Kn, right? This is in fact a new decomposition. So what is the condition? If K is normal in G, a finite group, and H is a Sylow P subgroup of K. If you can find a Sylow P subgroup of K, then the second factor of that normal group must be the normalizer. This is so easy because it is not so easy to find the second factor. But now it has become, due to Sylow's theorem, Sylow's theory, it's so easy because if K is one normal factor, and to find the other one, you take a Sylow P subgroup of K and then find its normalizer. That normalizer would work to get the entire G. Okay? So proof is since K is normal in G, so Kn is a subgroup of G. This is very trivial result. We have learned in our group 3.1 that if one of the subgroup is normal, then product is at least a subgroup of G, right? That is, Kn is contained in G, number one. Now conversely, you have to show that G is equal to Kn. Firstly, we have shown that Kn is a subset of G. Then take an element of G and try to show that this is an element of Kn as well. So for this, conversely, let X belong to Kn. Okay, now you have to show G. G is an element of. Conversely, let G belong to G, because the arbitrary element of G normally we use small g. And you have to show that G is an element of K. Okay? That G belong to capital G. Then since normalizer of H in G, so this implies H is contained in capital N, right? So and H is a Sylow subgroup of K, right? Number one. Also, H is a, H is a Sylow P subgroup of K. So H is contained in K. We will not use this. We will use this. H is contained K. Then GH inverse. This implies GH G inverse is contained in GK G inverse. Right? Okay, but the K is normal in G, so this is equal to K, but K is normal in G, so Okay, I am rewriting. Since H is contained in K, so G inverse is contained in GK, G inverse say number star, but K is normal in G, so GK, G inverse would be equal to K, where G belong to G, then star gives GH, G inverse is contained in K. Okay, see, the order of GH, G inverse is order of H, and H is a Sylow P subgroup in K. So GH, G inverse is also a Sylow P subgroup in K, right? But any two Sylow P subgroups in K are conjugate to each other. But H is a number, say, whatever, double star, I don't know the last number, what was the last number, so that's why I'm using star and double star. But H is a Sylow P in K, and order of GH, G inverse is equal to order of H, hence GH, G inverse is a Sylow P in K as well. Now by second Sylow's theorem, you know that any two Sylow P subgroups in a group G are conjugate to each other. So that's why you can find some Y belong to K, so that YGH, Y inverse is equal to H, right? But by Sylow's second theorem, these two are conjugate in K, hence X, G, H, G inverse, X inverse would be equal to H for some X belong to K. Just like previous lecture, we have used the idea in our previous lecture, a similar idea. So this implies XGH, G inverse, X inverse is equal to capital H. So this implies XG capital H, XG inverse is equal to capital H. This implies XG capital H is equal to H, XG. So this implies XG belong to normalizer of H in G, which was capital N, right? So this shows that XG belong to capital N. This implies G belong to X inverse capital N. Now, you see, this is a left coset, and X inverse is an element of capital K, and this is an element of capital N, right? That's why this is a subset of Kn, as X inverse belong to capital K. You see, this is a coset, right, of N. This is a left coset of N in K, because X inverse is an element of K, and here the set of all left cosets of N by K right? This is a set of all left co-sets and in K, and this is one of those. So yes, this is a subset of this one. So this implies G belongs to capital N. So this implies capital G is a subset of Kn, since G was arbitrary. Consequently, G is equal to Kn. Now you find an example, you take any example and try to justify this theorem. What was this theorem? This was a theorem to get an easy decomposition of a group G. You take a normal subgroup and then take any Sylow P subgroup of that normal subgroup. If K is normal in G and H is Sylow P in K, then you find the normalizer of that Sylow P, and that normalizer would be the second factor to decompose capital G like this. So if you have a normal subgroup and you can find a Sylow P subgroup of that normal subgroup, then in fact you are finding the decomposition of your given group. Okay students, try to understand the results. If you are finding any question or any mistake, let me know through your text messages. Thank you very much. Allah Hafiz.